So the first two, in fact, the first three, all are collated together because they all share this common equation of 3a becomes 2b. So for number one, it really is just a matter of stoichiometry. So let's look at the setup of the problem. For every 1 mole of A, you're going to create 2 moles of B and use up 3 moles of A. So that gives us 2/3 mole of B. Now that's how much B will be created. So A will go down, but B will increase because A is a reactant and being used up and B is being made. We want there to be a positive sign for the change in B, and that makes the answer B. If we look at the second one, we really got to look at what is the change in concentration of A over the time period from 10 seconds to 20 seconds. And we can take the bigger number minus the smaller number, and we come up with 0.0022 moles of A per second. Now realize this really should be a negative. However, it says in the question disappearance. So disappearance says, yeah, it should be negative. Don't worry about that. Kind of just give me a number. For number 3, we're going to need to take the same data table and this time look at 20 seconds and 30 seconds. And the setup is thus. So we can figure out how much the change in A is, and we can go back to the original stoichiometry, back from the equation in number 1, and figure out when that much A disappears from 20 seconds to 30 seconds, this is how much B gets made. So the answer there would be A. So for number 4, this is just looking at the numbers. So in between 400 seconds and 800 seconds, it goes from 0.057 to 0.046. That's pretty easy math. How much disappeared and divided by 400 seconds, and you get the answer of A. The previous question asked about iodide ion. This question asks about the S2O8 ion. So if we can figure out how much I minus disappears by the time you get to 800 seconds, then we ought to be able to figure out how much S2O8 disappears as well. So we look at going from the initial value of I minus to what it was at 800 seconds. We then say, well, if this is the molarity, and for every 3 moles of I minus, we're going to get rid of 1 mole of S2O8, then we can figure out the molarity of S2O8 that got used up. In the problem up here, it tells us that the initial value was 0.05 molar. So if we take the 0.05 minus the 0.0087, we get 0.041, and that answer would be E. So away from all the math. This is a conceptual problem that you wouldn't need a calculator for. What does a rate law look like when something is second order? And if I double the amount of carbon monoxide, what effect would that have on the rate? So if I plug in a 2 for the carbon monoxide, and it has an exponent of 2 because it's second order, then that means the overall rate would go up by a factor of 4, because increasing the amount of reactant makes the reaction go faster. Number 7 is just interpreting what you read. So if it's first order with respect to A, then A would have an exponent of 1. If it's second order with respect to B, then B would have an exponent of 2. In only one of the answer choices, choice C, has A with an exponent of 1 and B with an exponent of 2. For number 8, it says the overall order is 2. That means that we can make this assumption. Rate is equal to K times molarity squared. If we solve for K, plugging in molarity per second for rate, then we can get the answer of molarity over molarity squared seconds, which simplifies to 1 over molarity seconds, or molarity to the negative 1, S to the negative 1, the answer is B. For number 9 and 10, we're trying to write a differential rate law based on the experimental data. So for A, we need to pick 2 experiments where B is the same. So I'm going to choose experiment 1 and experiment 3. I'm going to compare what happens to the rate with what happened to the concentration of A. So my rate went from 2.83 to 25.47, and my concentration of A went from 0.273 to 0.819. Now, I know that the concentrations are going to get some exponent, so I can do the math here and get that 9 is equal to 3 to some exponent, and the exponent would be 2. Therefore, the order of the reaction is going to be 2. So letter B is the answer. For number 10, all we have to do is look at the data table. We need to pick 2 experiments where A stays the same and B changes. Well, that would be experiment 1 and experiment 2. But notice, even though B changes, B basically doubles, the rate has no change whatsoever. When a reactant changes and the rate doesn't change, we say that that is 0th order. So with respect to B, it has no effect. Even though it doubles, 2 to the 0th power would be 1. So the order of the reaction is 0. For number 11, it wants to know the overall order. That's easy. It was 2nd order with respect to A, 0th order with respect to B. Therefore, the correct answer is 2. For number 12, we need to go to the equation sheet that they use on the exam. These are the 3 equations that they give you. This first one corresponds to the 0th order integrated rate law. The second one has to do with the 1st order, and the third one has to do with the 2nd order integrated rate law. For 1st order, we want to use this middle equation. We know once we put it in slope-intercept formula, we're really graphing the natural log of the concentration of A versus time. That is the only one that will give us a straight line, and it will give us a straight line of slope negative K. Same type of question, except this time they're giving you the graph and they're asking you, hey, how do you know what the slope of the line represents? Well, again, since it's natural log, then it's going to be 1st order. And when you take that equation and you put it in slope-intercept formula, the slope of it is equal to negative K. For number 14, we're looking for a differential rate law. So rate is equal to K times ClO2 will have some exponent and OH minus will have some exponent as well. So all we have to do is pick experiments where the OH is the same, but the ClO2 changes. This time I'll use experiments 1 and 2 because the OH stays the same. We look and see what happens to the rate versus what happened to the concentration of the ClO2. And when you do that math, you get 9 is equal to 3 to some exponent, and that makes the exponent 2. So with respect to ClO2, this is 2nd order. For number 15, we're going to do the same thing, except for number 15, we need to pick spots where OH changes, but ClO2 stays the same. So we'll use experiment 2 and 3, and again, we just compare what happens to the rate to what happened to the concentrations of the OH minus ion. Once we simplify the math, we get, and 3 is equal to 3 to some unknown exponent, and you can see that the exponent for hydroxide here will be 1. So the correct answer is B. If we know that it's 2nd order with respect to ClO2 and it's 1st order with respect to OH minus, then the overall order of the reaction is 2 plus 1 is 3. What is the magnitude of the rate constant? Magnitude means just what's the number. Well, we have a rate law. We need to pick an experiment, and I'm going to pick experiment 1, and I'm just going to put in all the data. I'm going to put in the rate, I'm going to put in the ClO2 concentration and the OH concentration. I'll rearrange it so that K is all by itself, and I get an answer of 230. Another non-math question. These are the ones I like the best. Which of the following is false? So we'll just go through each one and say, is it true or not? Letter A. It's 1st order with respect to A. No, A has an exponent of 1, so it is 1st order. That's a true statement. The reaction is 2nd order with respect to B. It is 2nd order. That is true. So that is also a true statement. The reaction is 2nd order overall. Well, if A is 1st order and B is 2nd order, then overall it would be 3rd order. So letter C is wrong. Key here. So for number 19 and 20, we use this data table up at the top. We know that it's 1st order with respect to A. Since we know it's 1st order, I can use this integrated rate law. All I have to do is plug in some of the numbers from the data table in and see what I can get for the value of K. I picked 10 seconds. I plugged in the concentration at that 10 seconds and the initial concentration of 1.6. And when I solve for K, I get 0.1386. And that's close enough to 0.14. Now there are two ways to actually go around and figure out what the half-life of the reaction is. You could use this same integrated rate law and plug in 1.6 for the initial value and 0.8 over here, which would be half of it. And since we already know the value of K, you could solve for T. However, we don't have to do that. There's another equation that will help us do this. There's a half-life equation on the equation sheet. The equation sheet tells us that the half-life for a first-order reaction is this. We know the value for K is 0.14, and when we do that math, we get 5 seconds. Either way you did it, using the first-order integrated rate law or the half-life, you would have come out with about 5 seconds. 21, it's first-ordered with respect to A. So again, we would look at the equation sheet, find the first-order integrated rate law. You could plug in an initial value. You could plug in any one of the times and their corresponding molarity. However, if you notice from the data table, we know exactly when the half-life is. We start over here at 0.20, and 10 seconds later, it becomes 0.10. So we know that the half-life here is 10 seconds. So I can just use the half-life equation again. This time, I won't be plugging in for K. I'll be plugging in for half-life. And then when I solve for K, I'll get 0.0693, which is letter A. For number 22, we could use this equation, plugging in values from the data table and solving for what is the concentration at time t at 40 seconds. We take the value for K that we found from number 21 and plug it in. However, there is a simpler way to do it. In a first order reaction, the half-life is constant. So if we look up at the data table, we know that after 10 seconds, it goes from 0.2 to 0.1. Therefore, we know that the half-life is 10 seconds. I can use the half-life equation. And since 10 seconds is one half-life, 40 seconds is 4 half-lives. So all I have to do is take the initial quantity and cut it in half 4 times. And I get 0.0125, which is answer A. For number 23, you're just reading the reaction diagram and understanding what you're talking about. The activation energy for the forward reaction is from where you started to the top of the hill. The top of the hill is where we see the activated complex. So that's represented by letter X. If we were talking about the reverse reaction, then it would be X and Y. Because in the reverse reaction, you start way down low to the top of the hill would be X plus Y. For number 24, this is not a mathematical answer. It basically is saying which one would lower the rate of reaction and cause a decrease in gas production. Well, let's look at the answer choices. Sometimes it's easier to figure out what ain't the answer. If you increase the volume of acid, then really you're adding more reactant. That would actually make it go faster. If you increase the concentration, that also would make it go faster. If you decrease the temperature, if you decrease the temperature, we know that lowers the rate of reaction, so the gas production would actually decrease. So C is the answer. 25 asks us to analyze the graph showing the data of what happened over reaction. It's a straight line on the graph, so all we have to do is look at the y-axis and see what the units are. And it's the natural log of molarity. Natural log of molarity lines up with that first order integrated rate law. So it must be A, first order. None of these graphs are straight, and it's not asking you for order. It's asking you to understand the stoichiometry of what's happening in the equation. So if all the concentrations start out up here the same, the gray goes down some, but the black goes down much more. The hydrogen in the equation is going down by a factor of 2, while the oxygen in the equation is going down by a factor of 1. So the black line represents the hydrogen over time because it's being used up at twice the rate that the oxygen is being used up. So 27 is just analyzing those elementary steps. It's asking what is true about just the single oxygen atom. Well, an oxygen atom, your choices are catalyst, limiting factor, intermediate, or reaction inhibitor. This is just definitions. The oxygen here is made in the first step, and then it's used up in the second step. And that is the definition of an intermediate. It's not there in the beginning, and it's not there at the end. It's made in the first step, and then it's consumed in the second step. For number 28, again, you're looking at those steps, and you're trying to figure out which one is the rate determining step. You have slow and very slow. Obviously, the very slow step is the rate determining step. So all we have to do is look at the equation in step 1. There's 2 NO2s. So the rate law is going to be equal to rate is equal to K times NO2 squared. The fact that there's 2 of them in the elementary step, that's where we're getting the squared value. This is a reverse of number 28. In this one, they're giving us the rate law. So since the rate law is NO squared times hydrogen, we want to look and see which step has 2 NOs and a hydrogen as reactants. And step 1 has 2 NOs and hydrogen, so that agrees with the rate law. Now notice there's 2 choices here. A and B both say step 1. Hydrogen would be light. Sure, we'll have the greatest speed. Well, yes. However, that has nothing to do with why that's a rate determining step. It's because it matches up with the rate law. In number 30, this is not the intermediate question that we had before. This is which one is a catalyst. A catalyst, that is something that's there in the beginning and something that's there at the end. So it's almost as if nothing ever happened to it along the way. We have silver ion and cerium ion. We want to see who ends up being created again. And if we look, right here, silver ion is being produced at the end of the second step, but it's never consumed again. So the silver ion is there in the beginning at step 1, there at the end of step 2, and it's never used up again. The cerium ion is used up. In fact, there's 2 of them used up, one in step 1 and one in step 3. So since the silver ion gets regenerated, the silver ion is the catalyst.